Alright, so up until yesterday we saw how to visualize the matrices. We also saw some of the types of matrices, basics of matrices. Today we will continue with next topic, mainly the scalar and matrix multiplications. Okay, scalar vector multiplications. So we have for vectors already seen that when you multiply a vector with a scalar, certain changes happen to that. So we'll have to see what those are for today for matrices. So if I import again, this I'm import. You need not import, but my kernel had shut down in between. That's why I'm just re-importing. Okay, and from numpy dot random import rand int. Okay, this is a random module to generate to create certain random values for your um, matrices. So I'm gonna create two different matrices with rand int of, let me take values between 1 and 200. Okay, 16 values, and I'm gonna reshape them to be square matrices. Okay, and the same thing I will do for B as well. And if I print A, I have some values, random values. Print B, I have some other random values. Now if I do A plus B, okay, and B plus A, as you can see, matrix addition is commutative. Okay, and if you do so, hence you can conclude matrix addition is commutative. Okay, next you can also confirm, you can create um, one more here, more matrix here. Okay, likewise you can also visualize C here. And now if you try to add A plus B plus C, okay, that will give you some result. And then A plus B plus C, so that will also give you some result. And if you compare, uh, you can you can say matrix addition is associative. Okay, is this clear? Commutative and associative properties.
Yes, yes.
Okay, and now let some scalar s or maybe L is some scalar value. Let's just say 0.3. Okay, I will call it a scalar value. um, and now I want to take that, I want to create a different matrix wherein which I will want to have certain values, different values, not numerical values. I will mention 5 comma 5. I want to have a 5 by 5 matrix. So the reason why, we will see what will happen if you try to add or multiply a scalar to a matrix. Okay, so let us visualize D first. So this is our D. Okay, it has some random values between, so as you can see, plus 1, sorry, plus 2 and minus 2. No, even beyond minus 2. Okay, so it's some randomly generated values. What I'm trying to do is I will take this D, okay, and I will take this scalar, multiply it with np dot I. So basically I'm trying to create a identity matrix. So if I type like this, okay, this is a identity matrix, but to this matrix I'm trying to multiply this L into np dot I. If I do this, as you can see, the scalar has been multiplied everywhere, but every because other values are zeros, they remain zeros, but only the impact has happened on the diagonal. And now if I take this matrix, pay attention, because this concept you have to understand. So if I take this matrix and multiply to our original d, sorry, add it to our original d here, this I will take here and put it here. Okay, the values, if you pay attention, the values, uh, have decreased. So some places they have, actually the values have increased. Okay, when, because you have added, the values have increased by whatever bit. Okay, this process of increasing the values, see, here you are increasing, here also increasing, here also increasing. Okay, here also you have increased, here also you have increased, and rest of the values are same. This process is called as shifting. Okay, shifting the values of a square matrix. Now you are going to need this concept when you work on computer vision. Basically the point we are trying to demonstrate here is, when you multiply, sorry, when you, okay, let me do one more thing before I explain you. Okay, if you directly add the scalar value, which is your point 0.3, to d, if you pay attention again, so this is your d and this is your values, so it gets added everywhere, so your value is increasing everywhere. Okay, so this is your direct addition, and if you directly multiply, so it gets applied to, scalar gets applied to the complete matrix everywhere. This is your normal multiplication, but this one is called as shifting the values, shifting process. Okay, for matrices, I'll come back to this process. Okay, why we need shifting and all, when you talk about padding and when you talk about changing the attributes of existing image, there we will make use of these concepts. But for now, just understand that if you take a scalar value and if you try to multiply it with a matrix, okay, you can get this same expected result what you would get. So basically scalar gets added to all the elements of matrix and it gets multiplied to all the elements of matrix. But if you want to multiply only, only want to change the diagonal values, retaining all other values as same, that process is called as shifting. Again, we'll learn this in computer vision. For now, just park it. Okay, so this is your scalar matrix multiplication. Is this clear?
So Sadik, whatever value you have applied under that I
Mm-hmm.
file,
Mm-hmm.
it's random, right?
It's
As per
random,
requirement,
yeah.
you can
I
change it.
need, yeah, I was trying to have a square matrix, so that's why it's a random. So this could be 3 comma 3 also. Okay.
No, I am talking about that I. Okay. Whatever kind of size of your matrix is, will apply the same in the I also, right?
Yes, yes, same value will apply here and here. Okay, and here also, everywhere it's the same thing. Okay, so if I execute this, okay, so you get
Okay.
the
Yeah,
same thing. Yeah,
got it.
but in realistic I mean real world scenario, you're not going to use 3 or 5. You're rather going to have an image of at least 256 by 256, which means your matrix will have huge number of values. Okay, something like if I take this and put a 256 value here, 256 by 256 value, so this is your original image. You can't even visualize here on the display, but if you notice these dots indicate there are so many repeating values. And if you uh, want to know the shape of this, Okay, if you want to know the shape of this, it will say 256 by 256. So 256 values like this exist for your image, and that is only for color R. Okay, because there is RGB, right? So three
Hmm.
combination of three will constitute an image. So you'll have 256 by 256, or again, so likewise you will have 256 by 256 for three different colors. But even these 256, sometimes you may get different resolutions. Okay, our computation limitation of is such that nobody can compute it for 2 mega. The resolution for what is the HD image is 1980 by 1080, right? We don't have computation capability to do all the images in this value and make use of neural networks for these values. That's why we will have to shrink it down to either 256 by 256, or we will even further reduce. Sometimes we will even reduce to 32 by 32 or 16 by 16, that way. Okay, basis based on the requirement. But this I have this value just to show you, I have taken randomly. Okay.
Yeah, so what is the purpose of changing the value? Only diagonal values changes.
Yeah, this, that's why I said this I will explain in computer vision. Okay, so shifting is for certain manipulations you require only the diagonal elements to be changed. Okay.
Yeah.
Yeah, so there is a lot of concepts there, so we'll learn all of those. But it's good to know that I mean, even if you have a slight idea of this beforehand, then it will come in handy. Okay. All
Okay.
right, so if additive property for addition, uh, commutative property, associated property is clear. But we will also see for multiplication. Okay, matrix addition is associative, we have established. But I'll take the same examples: A and B and C. Okay, and if I multiply A into B, first of all, to multiply you need to know the dimensions. So number of dimensions, that's why I have deliberately taken 4 by 4, so that I can easily do the multiplication. But number of rows, as you know, the rule of matrix multiplication is the number of um, okay, rows into columns you multiply, right? So that's why the shapes should be same, right? So if for matrix A, m into n is the shape, and for matrix B, shape should be n. So basically the number of columns that exist in A should be the same as rows in B. Okay, and if you want to multiply with C again, okay, again it should have the same. So number of columns of B should match with the rows of C. Okay, so this is a rule for multiplication. But because I have taken all m and ij are equal to me, so it doesn't matter. We can go ahead and check. So if I do A into B, I'll get this. Okay, if I do A into B, okay, and B into A, okay, I'll get the um, same values. But this is your normal multiplication, right? But if you try to apply, okay, so okay, maybe I think we should take simpler matrices, right? So that way we can easily do. Let's do
Yeah.
that, because this is, again, we can't establish if it is actually multiplying. um, okay, so I will take this as 2 3, okay, 1 4. me print a, b is equal to 1 2 2 1. Okay, c away again, I will take it as 2 comma 4 2 comma 3. Okay, so you have now let's multiply a into b. Can't be multiplied because they are lists. Okay, fine, no worries. So I will make it as np dot array of. Okay, and here also it is b is equal to np dot array of. Okay, um, np dot array of. Okay, okay, so this is your normal multiplication. This is nothing but your um, we will come to this big okay, anyway, this is called as Hadamard. Okay, multiplication. So Hadamard multiplication, we also have a calculator for that. Hadamard multiplication is nothing but you are multiplying elements of the matrix directly. Multiply together the elements that lie in the intersection of first row and first column of each matrix. Okay, so you have a calculator also. Here you have, I've taken the rows and columns. Just for the example, I have given a1 a2 b1 b2, some values I have given here. Okay, and here also I have given the same values, so you will get the matrix. So basically what is happening is 2 into 1 is first element 2. Okay, 3 into 2 is 6, second element 6. Okay, that way element wise multiplication. So if you notice 12, 4 into 0 is 0. So so Hadamard multiplication is nothing but element wise multiplication. Okay, element wise multiplication, but that's not how our matrix multiplication works. So when you do a Hadamard multiplication, you can establish that these are commutative, and I'm very sure you can even establish Hadamard multiplication is associative. But that's not what we are interested in. What we are interested in is the actual matrix multiplication, which for which we have matmul. Okay, okay, and this is also um, called as a comma b. Okay, dot. So this is also called as dot product or um, matmul. So either way, I prefer matmul because at least the naming convention is the same, matrix multiplication, right? So that's why I just use that. Anyway, so when you do the matrix multiplication, you can easily see the results are different, right? Now that the results are different, you can say matrix multiplication is not commutative. Okay, is this clear?
Yes.
Okay, and if you do the math again, so because it's not commutative, it will not be associative also. Okay, um, so I will quickly verify that as well. Okay, np dot matmul of a comma b we have already taken. Okay, and for this I'm gonna do, on top of that I'm gonna do a matmul again, np dot matmul of. Is this clear? First I'm multiplying a into b, and whatever the result gets, for that I'm multiplying with c. Okay, and here what I'm doing is I will take matmul of A first, and then I will make the matmul of um, B comma C. Now, so if you do, okay, so somewhere I've missed the bracket. 1 2 3 1 2 3. Okay, fine. One more bracket is required. Okay. Oh, luckily, associative, for associative property, matrix multiplication is not commutative, but it is associative. Interesting. Uh, okay. Okay. Matrix multiply. I thought it was going to be not associative, but anyway. So as you can clearly see, the results are different. But when you do a matrix multiplication of first you combine these two, and to that you multiply C, and here first you are multiplying A with whatever the product of B and C. So finally you can establish matrix multiplication is associative. Is this clear? Any doubts between Hadamard and multiplication and matrix multiplication?
No.
No. Okay. All right. So you remember the scalar that we took previously? Um, for that, we have another property that we need to check. Let S be my some random uh, random matrix which consists of values between 1 and 10, and if I finally print that matrix, I'll get an array of 8. Okay. Now what I'm trying to do is I'm trying to see, this is a vector. Okay, this is a, okay, let me have two values. Let's try with this. So this is a vector. Now what I'm trying to do is I'm gonna try to multiply this a plus b. I got some value. I took a vector, okay, and I took this a and b. To that I have added and multiplied. Now what I'm trying to show you is if you multiply s into b, you get the same result. So essentially when you take a vector, okay, this is, now we are talking about vector, not scalar anymore. So when you take a vector, you multiply with the matrix, okay, such that you are multiplying with the addition of two matrices, okay, and compare it with individual multiplications of vector to those individual matrices, and then add them, so you get the same result. So that way I can say this equals to this. So you get the true value. This is another property. Okay. Clear? Any doubts in this?
No.
Okay. All right. So the next thing is we have something called trace of a matrix. Okay. See all
Here,
this.
Sadik,
Yeah.
yeah, here when we are multiplying S
Uh-huh.
to A, it is again a Hadamard multiplication, no? It's not a matrix multiplication
Yeah. Yeah.
because
Correct.
yeah, yeah, I mean, and so for when it is actually S is a matrix of order, is it a it's a kind of vector, right?
Yes. Yes.
S is a kind of vector actually, no? So we are multiplying this matrix by a vector.
Yeah.
Uh, and if we see, it's either we can call it as a row or column vector because we
Correct.
cannot see that. Yeah?
Yes. Yes.
And so I wonder how this multiplication is like taking place to A. Can we just print A there? Like we
Sure.
just get to know how when we are multiplying A,
Yeah.
by this vector, how
A.
this transformation is
This
basically
is
taking
B.
place.
Okay.
Okay.
This is A
Uh-huh.
plus B. Okay.
Yeah, yeah. I
And
mean,
now you can
S
do the calculation. 4 into 3 is 12 here. Okay.
4 into.
Is the normal multiplication, because
Okay, okay,
number
okay.
of
4
rows
into 3.
and columns match, right?
3 is 24. No, number of,
Okay, see,
because,
4 into 3 is 12. Okay,
right,
8 into 5 is 40. Again,
40, okay.
4 into 3 is 12.
12
Again,
and
8
again
into
40.
40.
Okay,
Okay, so basically,
okay,
row one
okay.
value of this is being multiplied to this, and second value is multiplying to the second value.
Mm-hmm. Okay, okay, okay. So, fine, fine.
Yeah. Okay,
Thank you.
and next is trace of a matrix. Okay, trace of a matrix. See, this is that's why I said this is a very good website. So you have basic definitions and concepts explained here. Trace of a matrix is nothing but sum of its diagonal elements. Okay, and trace, when you take a trace, you have its own properties. We will not be validating this because these are already established truths. So trace is nothing but sum of its diagonals. So how do you calculate the trace directly? So for that we have let me take the A matrix only. Okay, this is my A matrix. So diagonal here is 4 plus 2, right? So you can directly call diag, np dot diag of A. Okay, so this is the diagonal of, I mean, this is the diagonal of the matrix. And to calculate trace, so you have directly, you can calculate the trace directly. Okay, so when you want to how this translates is, when you want to do some sort of compression techniques, or when you want to validate, do some image validation. Okay, all these techniques will come there, all these calculations will come there. Okay, so for now just understand, you don't have to worry much. For now just understand that trace is nothing but sum of diagonals, and that can, for that we have a direct function. Okay, is this clear? Trace of a matrix.
Yes.
Okay, all right. So the matrix multiplication also we have seen, right? And one more thing I wanted to show you is, let's just say you want to okay, one moment, the next topic I'm checking. Okay, all right. So for dot product, let me check this. Okay, np dot, one second. So np a comma b, I wanna just calculate this. A. Okay, yeah. So I was trying to so you can do a dot product with at symbol as well. Okay, dot product or matmal. Okay, matmal, whatever you want to use. But the simplest way is using a at b. Okay, so you can do the dot product by doing this as well. And we have something that we need to understand. We call it live t. Okay, I mean, this is just abbreviation uh, that mathematicians have tried to establish. Let's just say you had a matrix L, I, V, E. These are separate matrices. Okay, so what we are trying to say is, if you take this entire separate matrices L, I, V, E, okay, and then you take the transpose of it, this should equal to, okay, E multiplied by its transpose, okay, and V multiplied by its transpose, okay, and I multiplied by its transpose. This is your homework. Okay, this I'm not going to do, because just you just have to call the matrices, define the matrices, take the transpose, and you the way how to take the transpose is, if A is my matrix, A dot transpose, if you call A dot T, you will get the transpose. No, compare the A and see, 2314 2134. Okay, so you A of transpose can be taken just by calling transpose, or np dot transpose of A. Okay, np dot transpose of A. You get the same thing. Either you can call directly A dot T or this. So this is your homework. I want you to just validate this, result. So basically create some 2 by 3 or 3 by 3, create a square matrix for better easier multiplication. Create 2 by 2 or 3 by 3 matrices for LIVE, just like how we created np dot array. Create manually. Okay, don't use
Hmm.
functions. That way you'll get some idea on how to create vectors as well. So create those and validate these results. Is this understood? Is the question understood?
Yeah, just want to know now. We see when we are actually taking the dot A dot T,
Hmm?
so it is the matrix multiplication and not what is that multiplication you called this as earlier? It's a word
Hadamard.
like
Hidamat.
element Hadamard multiplication. This is the matrix multiplication. So basically, we can carry out the matrix multiplication by three ways. What I see here,
Mm-hmm.
or what I suppose, what
Mm-hmm.
I understand, it is like np dot a comma b is
Mm-hmm.
one method. Then matval is the second method,
Mm-hmm.
and a at the rate b is the
Mm-hmm.
third method. Is
Okay.
it
Yeah.
right?
You take this as homework. Okay. Either do Hadamard multiplication or do dot product and validate. Okay. I'm leaving it to you. Find out which
Okay,
multiplication works for this. That is your homework. Okay.
okay. Yeah, yeah,
Okay.
sure.
And
Thanks.
if you want to do, I will give you a hint also. If you want to do the multiplication in a very simple way, what you can do is L at I at V at E. So this will give you this first term, and to that you are taking the transpose. So you add this completely, and then do dot T. Okay, don't yeah. So if you do this, you will get the first term. Now you apply that to the second term. Okay, so just a hint I will mention here. Um, Simplest way to calculate is using at underscore, so which is your dot product. Okay, so just do a dot product, and or you can apply np dot dot or np dot matmul, whatever. So this, take this as hint and verify this result. Okay.
Yes.
Yeah, yeah, sure, sure.
Okay,
Thanks.
all right. So okay, this is done. And vector multiplication also we saw. The next one is uh, matrix transformation, also we have seen in the previous class. Basically when you take a, because matrix is a combination of vectors, the same rules apply for matrices also, which means when you want to increase the size of a matrix, basically do a rotation or stretching, you just multiply it with a another matrix. Okay, that gets stretched. Okay, the same rules, and it's just that we won't be able to visualize it. The problem with the visualizing matrix is we can only see it as colors, but the same rules apply. Stretching, okay, moving, okay, all those things apply here also. Then the next thing is we'll see some identity, um additive multiplicative rules for identity matrix. Okay, we have to establish, again we have to establish this relationship. This is again required for our various things, for minor calculations, for orthogonalization, and mainly for determinants. Okay, so that's why we just want to validate this one here again for this rule. Okay, let me. So this I think we already know, but we just want to. um, so if I take, or maybe I can take np dot I of 2, and I can print that I. So this is what it is. If I do ai a at I, okay, I at a, so they are the same. So hence you can say, if I say a at I minus I at a, okay, so that will be a 0. This come, okay, this I will delete. So now you can say it is equal to, actually it is equal to 0, it's not equal to a. Why? um, One moment, I think what kind of multiplication we are doing here. Okay, so hold on. Is this
It's
equal to
math,
a?
man, right?
No. This is equal to. Okay, I'm sorry, my bad. So ai minus ia, this itself is wrong. Actually, this has to be equal to 0. Or in other words, or ai should be equal to a. I wrote it wrong. Okay, so now we know. So we have to do dot products only. Okay, mostly dot product is what we will use throughout our journey for might be data analysis, might be machine learning. Okay, preferable multiplication is dot product only, which is your proper matrix multiplication. So now you can conclude ai minus ia equals to 0, which you can see here. And as you can see, a into I equals to a. Okay, so here that also you can do. I equals to, equals to a. If you compare, you'll get everything is 2. Okay, any doubts with this? I mean, this is straightforward, there is nothing
No,
out of
no, it's fine.
ordinary. Yeah.
Yeah.
Okay, so we will stop the class here. Okay, and please finish your breakfast and come back at 9:15. Is that okay for you?
Yeah.